In previous sections, in previous classes, we discussed about the noise topic. So we discussed about the noise types also, and the noise calculations in amplitude modulation systems, and the noise calculations in angle modulation systems. In previous class, we discussed these two topics. So the effect of noise in amplitude modulation systems. So we have different types of amplitude modulation systems. Those are DSPFC, DSBSC, and SSBSC. And the noise calculation in angle modulation system, that is in frequency modulation and phase modulation, and the threshold effect in frequency modulation. So these noise effects we can calculate by using the signal to noise ratio and the figure of merit. So these are the topics about noise we discussed in the previous classes. Okay, so now in this class I'm going to discuss you about pulse modulation introduction. So we know that the modulation is classified into two types: continuous wave modulation and pulse modulation. And the continuous wave modulation is again classified into two types: amplitude modulation and angle modulation. And the angle modulation is further classified into frequency modulation and phase modulation. And we have another class of classification is the pulse modulation. So this pulse modulation is classified into two types: analog pulse modulation and digital pulse modulation. So what is the difference between these two techniques is nothing but here the pulse, the carrier pulse is carried the analog information, that is nothing but the analog pulse modulation. If the carrier pulse carries the digital information, that is called digital pulse modulation. In analog pulse modulation, whatever the applying information signal, that is continuous in nature, but the pulse, we are taking for the modulation, the carrier will be in pulse. The carrier will be in pulse form. So again, the analog pulse modulation is classified into three types: pulse amplitude modulation, and pulse width modulation, and pulse position modulation. And the digital pulse modulation is classified into pulse code modulation and delta modulation. So what are the advantages of pulse modulation is nothing but here the transmitted power is not in continuous nature. The transmitted power is in pulsed in nature. The transmitted power is pulsed in nature. So that is the advantage of pulse modulation when we are comparing to the continuous wave modulation. Okay, so in pulse modulation, the most important technique that is the sampling theorem. That is the sampling theorem. What is sampling? Sampling is nothing but representing a continuous time signal into discrete time signal by taking the sufficient number of samples to represent the original signal. That can be stated as the sampling theorem. So sampling theorem is nothing but converting the or sampling the continuous time signal into the discrete time signal by taking the sufficient number of samples to represent the original signal completely. To represent the original signal completely, how many number of samples we have to take, that is depending on the sampling theorem. Okay, so here the number of samples should be, that is the sampling frequency is always greater or equal to 2 FM. So to do sampling, the sampling frequency should be always greater or equal to twice the message signal frequency. So that is Fs is greater or equal to 2 FM. For example, we are assuming here the continuous time signal, it contains the highest frequency component is FM. So the sampling frequency is always should be greater or equal to twice the highest frequency component in the message signal. That is nothing but sampling frequency. So always that sampling time and sampling frequency are inversely proportional, and this sampling time is always equal to the 1 by 2 fm, 1 by 2 fm. This is called the sampling time. So it is nothing but the uniform intervals. So the uniform intervals are always less than or equal to 1 by 2 fm, 1 by 2 fm. So that is nothing but the sampling theorem. What is sampling theorem? A continuous time signal. So that may be recovered back by using the samples. These samples, these sampling frequency always should be greater or equal to FM. FM is nothing but the maximum frequency component in the signal, continuous signal or message signal. FS is nothing but the sampling frequency. Fs is nothing but the sampling frequency. If you want to represent a continuous time signal in discrete time signal, you have to consider the sufficient number of samples to represent that original signal completely. So you have to consider the sufficient number of samples. So here the sufficient number of samples are more important to represent the complete signal. To represent the complete signal, this should be done by using a sampling theorem. So that sampling frequency should be greater or equal to 2 FM. Should be greater or equal to 2 FM. So this is the proof of sampling theorem. Just here we are considering an example. So here x of t is nothing but a message signal. X of t is nothing but a message signal, or else what we call it as a continuous signal. What we have to do, we have to convert the signal into the discrete time signal by sampling. So to do sampling, what we are assuming here, a impulse train, that is delta of t. Impulse train, that is delta of t. So here you may observe this is the sampling train, sampling train, impulse train. So this one is impulse train. Here the samples are taken apart with a distance ts, So this is impulse train and this is continuous signal. If we multiply both these signals, you will get the discrete time signal. So here what we are assuming here, the impulse train with amplitude 1 we are assuming. So here each and every point of the continuous signal is multiplied by this impulse train. You will get the discrete time signal here. You will get the discrete time signal here. The discrete time signal what we are representing is y of t. So y of t is equal to, in mathematically we can represent x of t into delta of t. So here x of t is the continuous time signal and delta of t is the impulse train. Here the impulse train is periodic signal. So here delta of t is periodic signal. We can represent it in Fourier series representation. So this is the Fourier series representation of the impulse. Here an and bn and a naught are called the Fourier coefficients. So these Fourier coefficients we can calculate by using these formulas a naught, an and bn. Finally you will get a naught is equal to 1 by ts and an is equal to 2 by ts and bn is equal to 0. So if you substitute these coefficients in delta of t, so you will get delta of t is like this, 1 by ts plus summation n is equal to 1 to infinite 2 by 2 ts into cos n omega st. N is equal to, it will be varied from 1 to infinite. So if you substitute this impulse train in the original expression, y of t is equal to x of t into delta of t, you will get the discrete time signal or the sampled signal. So that sampled signal is 1 by ts x of t 2 cos omega st x of t. Here omega s is nothing but the sampling frequency. Omega s is nothing but the sampling frequency. So here you may observe the spectrum of the message signal and the sampled signal or discrete signal. So here x of omega. So if you apply Fourier transform, you will get the frequency domain equivalent. For x of t, we will get x of omega. So this represents the bandwidth, upper cutoff frequency and lower cutoff frequency. These are the band of frequencies which contains in the input signal or continuous signal. And this is y of omega, so you can obtain this y of omega from the y of t from the time domain. If you apply Fourier transform, you will get y of omega. So we have the frequencies 0 omega s, 2 omega s, minus omega s, and so on. So these are the this is the sampled signal or the discrete time signal, and it will be converted to the frequency domain. So ivi manaki frequency domain representations. Okay, so this is nothing but sampling theorem. You may observe, if we consider the sampling frequency, if it is greater than 2 FM, how the spectrum is looks like, and if Fs is equal to 2 FM, how the spectrum, and if Fs is less than 2 FM, that is called undersampling. How the spectrum is looks like. So if the sampling frequency is very much less than the 2 FM, you will get the aliasing effect. You will get the aliasing effect, and this sampling is called undersampling. And this sampling is called undersampling. So this aliasing effect can be removed by Fs should be greater than 2 FM. So what is the aliasing effect? Is nothing but the high frequency component in the signal. It takes the identity of the lower frequency component. Because of that, so we have overlapping frequency spectrum is obtained. Because of that, we get the overlapped frequency spectrum, that is called aliasing effect. So this can be removed by considering Fs is greater than 2 FM, or if you have to choose the aliasing filters. Aliasing filters means here you have to choose the low pass filter to remove the high frequency component. So these are the spectrum representations. See here, if FSC is very much greater than 2 FM, so we have the spacing between the spectrum intervals. And if Fs is equal to 2 FM, and it looks like this, and if Fs is less than 2 FM, you will get the overlapped spectrum. So between the so here the cycles will be overlapped. Okay. So, and this Fs is equal to 2 FM is known as Nyquist rate, and the time is called a Nyquist interval, and the time is called Nyquist interval. This is sampling theorem. So what is sampling? Sampling is nothing but representing the continuous time signal into discrete time signal by taking the sufficient number of samples, and by using these samples you have to get back the original signal. If you take the sufficient number of signals, you will reconstruct the original signal. Okay, so this is about sampling theorem, and we have different types of samplings. So one of that one is impulse sampling, and another one is natural sampling, and another one is flat top sampling. So these are the three sampling techniques. So impulse sampling, natural sampling, and another one is flat top sampling. Okay, so what is impulse sampling? So here, whatever the signal you want to convert into discrete time signal, you should multiply that signal with the impulse train. Impulse train, it is a periodic pulse train, and it is also called ideal sampling. And it is also called ideal sampling. Why? Because it is not possible practically, means here in the graphical representation, here the width of the impulse is it cannot be zero, because the pulse width here cannot be zero, but practically there is a pulse width exist. So practically impulse sampling here is not possible, because here the pulse width cannot be zero. So see here x of t, this one, and it should be multiplied by the delta of t impulse pulse train. You will get the sampled version of this continuous wave signal, and this is also called sampled signal, or also called discrete time signal. And another one is natural sampling. Natural sampling is nothing but here a pulse train will be generated having some width, that is called pulse width. That is called pulse width, and it should be multiplied by the continuous wave signal. You will get the sampled signal here. You will get the sampled signal here. Excess of t sampled signal is equal to, and whatever the signal you want to convert, that is called x of t, we want to convert, and s of t is nothing but the pulse train. S of t is nothing but pulse train. సో ఇక్కడ ఎక్స్ ఆఫ్ టీని దేంతో మల్టిప్లై చేస్తున్నాము, పల్స్ ట్రైన్ తో మల్టిప్లై చేస్తున్నాము. అండ్ దిస్ ఈస్ ద సింపుల్ సర్క్యూట్ టు గెట్ ఫ్రమ్ దిస్ యూ కెన్ గెట్ ద న్యాచురల్ sampling. Here x of t is input, and x of here is switch to control the sampling, and this x of t is multiplied by this pulse train, this pulse train, and you will get the sampled signal here. You will get the sampled signal here. So here you may observe here the sampled signal amplitude is not constant. Not constant means it is not flat. It seems to be looks like this. Here the amplitude during this interval is not constant. It is varied. It is varied. Here means here the sampling is sampled output is not a flat top. Not a flat top. And this one you can represent here. What we are saying is the pulse train. So what is pulse train? S of t is the pulse train, and x of t is the message signal. So for the pulse train, we are assuming this Fourier series expansion, that is a rectangular pulse. You can represent like this. So C0 and Cn are the Fourier coefficients. If you find this, and if you substitute these S of t in the sampled signal, you will get excess of t is like this. And after applying the Fourier transform, you will get the time domain into the frequency domain, and it will be looks like this. Here you may observe here the frequency spectrum is the function of a sinc function. Here the message term is scaled by the sinc function. Which is not the case in the case of instantaneous sampling. That is the drawback in the natural sampling. So we have the spectrum looks like this. Okay, another classification is flat top sampling. So for example, during the transmission, we have the possibility to get the noise. That noise will be added at the amplitudes. So during this transmission, this noise is introduced at the top of the signal. So you can easily remove, if the top is a flat top, you can easily remove that noise from that flat top. So this is the best sampling technique. So that is nothing but the flat top sampling, and it is also called a practical sampling technique. It is also called a practical sampling technique. And here we are considering the X of t is the baseband signal or message signal, and this is the pulse train. And what we will get here, Y of t is the sampled signal, and you may observe the samples are flat. The sampled signal at the output is the flat top sampling. Is the flat top sampling. To get this flat top, to get this Y of t, what you have to do, if you want to obtain the sampled signal by the convolution of the rectangular pulse H of t with the ideally sampled signal, you will get the sampled signal. So this is the circuit to obtain the flat top sampling. If you reconstruct, you will get like this. So for flat top sampling, so the train of impulses you should consider like this. And the signal S of t can be obtained the multiplication of the message signal with the train of impulses. You will get S of t here is like this. So now the sampled signal G of t is equal to X of t is convolution with the H of t. S of t is in convolution with the H of t. You will get G of t is like this. And if you apply the Fourier transform, you will get G of f. So here the spectrum of flat samples you may observe. So here the drawback is we have aperture effect. You may observe the spectrum of the flat top. So going on high frequencies, so what we have here, it will be attenuated. If the frequencies are increasing, so the spectrum will be attenuated. Upper portion of the spectrum will be attenuated. So this is nothing but what we call it as an aperture effect. Means in flat top sampling, so an amplitude distortion in the reconstructed signal X of t from the G of t. So this distortion attenuates the higher frequencies or upper portion of the spectrum, message signal spectrum. Means it acts as a low pass filter. Means it attenuates the higher frequencies. Means here in this spectrum the higher frequencies are attenuated. That effect is called aperture effect. So how can we minimize that aperture effect? We have to use a reconstruction filter for the compensation, and you have to use an equalizer. So you have to use an equalizer at the receiver end, need to compensate the aperture effect. So that receiver contains a reconstruction filter and a equalizer. So equalizer is in cascaded with the reconstruction filter. So for cascading means we have to multiply. You will get the transfer function of the equalizer. Transfer function is nothing but output by input. You will get the transfer function of the equalizer. So at higher frequencies, the higher portion of the spectrum will get attenuated. That is called aperture effect. We can minimize that aperture effect by using a reconstruction filter and equalizer. So because of that, you can minimize the aperture effect. Okay. And we have pulse in pulse modulation, we have different types of classifications. Those are pulse amplitude modulation, pulse width modulation, and pulse position modulation. Okay, so in pulse amplitude modulation, we have again classified into two types. One is for the single polarity PAM and double polarity PAM. So single polarity PAM means it allows the only signals having the one polarity, and double polarity PAM means the pulses having the both the positive and a negative polarities. In single polarity means the pulse have only single polarity, that is the positive polarity we are considering here. Okay, so these are the pulse analog pulse modulation techniques. Analog pulse modulation techniques. What are those? Pulse amplitude modulation, pulse position modulation, and pulse width modulation. Okay, so this is all about the pulse modulation introduction. So what is pulse modulation? So generally we know that a modulation is generally classified into two types, continuous wave modulation and pulse modulation. Here the carrier is pulse, that is called a pulse modulation, analog pulse modulation. And but in continuous wave modulation, both the carrier and the message both are continuous in nature. So before going to that, so what we have to do, we have to convert the message signal or whatever the continuous signal into discrete time signal. So sampling theorem is nothing but representing a continuous time signal into discrete time signal by taking the sufficient number of samples, and by using these samples you have to reconstruct that original signal. So you should able to represent by using these samples, so you should able to represent the original signal. Original signal you should able to represent completely if you consider the sufficient number of samples. If you consider the sufficient number of samples. So to do sampling, what are the conditions you should follow? You have to consider the sampling frequency. You have to consider the sampling frequency that should be always greater or equal to twice the message signal frequency. Here FM is nothing but the highest frequency component in the message signal. FM is nothing but highest frequency component in the message signal. For example, if we consider FS is less than 2 FM, so you will get the aliasing effect, that is nothing but overlapped spectrum you will get. Overlapped spectrum, that is called undersampling. What we call it as undersampling. If in undersampling you will get the overlapped spectrum. So aliasing effect is nothing but the high frequency component in the spectrum, and taking the identity of the lower frequency component in the spectrum. So that is called this aliasing effect. So this effect can be removed by choosing the FS greater or equal to 2 FM, or else you have to use the anti-aliasing filters. Anti-aliasing filters. Okay, and we have different types of sampling techniques, ideal sampling or impulse sampling, natural sampling, and another one is flat top sampling. Ideal sampling is practically impossible because here the width of the pulse ideally we are assuming is 0, but practically it is not possible. So you have to consider some ways. So you will go through the natural sampling, but in natural sampling the amplitude of the sample signal is not constant. So you will get a flat top, so you go through the flat top sampling. Flat top sampling. In flat top sampling we have a aperture effect. You want to minimize that, you have to consider an instruction filter along with the equalizer. Okay, so these are the classifications, and this is all about pulse modulation, analog pulse modulation introduction. Analog pulse modulation introduction. Okay, so next class lo PAM, so PPM, PWM గురించి next class లో మనం discuss చేద్దాం. ఓకేనా?